So, in the last lecture, I introduced this idea of measurement based quantum computing, and this is a different paradigm compared to the circuit based construction, and it's unusual in the sense that only measurements are used in tunable directions. That is a concept you need, but other than that there are no other transformations on the logic states. And it came as a surprise when it was introduced, and the people who did that were Rausendorf and Briegel, and they did the complete job in the sense that introduced the concept and proved that it is perfectly equivalent to the usual logic circuit implementation. So, last time I defined the set of operations which are involved in this process, and I gave a very simple example of how it can be used to teleport a state from one location to another location, given that there is a link which is defined by the control Z operations between these two locations. So, today I am going to extend that concept to the general framework where you can implement any arbitrary logic gate. Okay. And that is in some sense easy to understand. To modify that teleportation concept and give a explicit description that instead of just copying the state, how you can apply an operator also by the same circuit by using a different measurement procedure. Okay. So, that is where I am going to start. Let me write down some of those basic operations again. So, there was this measurement operator with arbitrary direction in the xy plane, and which is a linear combination of Pauli matrices along the equatorial plane of the Bloch sphere. It has eigenvectors which it will project because you are going to measure this operator. So, these eigenvectors are going to denote by plus or minus, and they were rather straightforward combination of 0 and 1, but with a phase thrown in between. Okay. And yeah, I should write the eigenvectors, eigenvalues. The same plus minus sign whatever appears over here. It's a matrix with determinant -1 and trace 0. So, eigenvalues are plus and minus 1. So, we are going to use this over and over again. Every time you measure, the state will be projected along these directions. Now, we can proceed step by step. And the first thing is to just generalize this qubit teleportation to what I am going to just call gate teleportation. That not only the qubit is transferred to the another location, but it's rotated, and whatever that rotation is will be the gate defined in this label. So, for the teleportation circuit, the structure was very simple. One state was initialized to some psi, and the other state was initialized to plus, and we applied so initial state is the control Z, which describes this link applied to psi and plus. That's what we used, and I wrote down some generic description that psi is equal to A0 plus B times 1. Okay. Fine, I will stick with that. And now, instead of measuring the theta equal to 0 version, which is what I did for teleportation, I am now going to choose general theta. And so, you can ask what will happen. So, let me expand this thing out. So, this thing is now going to become A times 0 plus B times 1 minus. Minus sign comes from this control Z. That is not affected at all. The initial state is identical in both the situation. I have to be consistent in the notation. Okay. So, now measuring m theta projects the state using the standard dot product, but I have to remember that this is the cat vector, and I project with the bra vector, and that change is important because it will flip the complex number in a phase. Okay. So, I am going to get two outcomes with some probability. I am not worried about the probability because all the solutions are ultimately going to get merged into a single combination, but I want to know what will happen to the projected direction. So, this is a 2-qubit state. I project it 1 qubit with this particular factor, the other qubit is going to survive. What is that surviving state? Well, I take this dot product, and there are two possibilities. I will just write down whether it is the plus component and minus component. So, there are two options. So, I take dot product of this with these 0 and 1 state. So, let me just write down what happens. When I take a dot product of this with the vector, first vector, it is A, then 0 with 0 is just going to give 1, and then the second half is going to survive, which is this particular vector, and then the term coming from B, 1 is going to get dotted with this particular half. So, it will be e raised to I theta sign change, because this is a complex conjugate, and this is the minus component of the second qubit, and this one now will look very similar, except that the theta minus has a negative sign. So, it will look like this direction. There are actually all normalization factors, but I am not bothered about, they are basically root 2's floating around, but they are all going to get merged, and you can insert the root 2 later stage wherever you want algebraically correct formula, that is all right. So, now let me just rewrite this stuff by expanding out this plus and minus in the original computational basis of 0 and 1. So, this is 0 plus B. So, A and B, B e raised to minus I theta times 0 and plus A, the minus one is minus component times 1. And this is the same thing except for a change of sign. So, it is another combination. And these two are related by sign change of B, or if you look at it again, you can say that this is related by interchange of 0 and 1, which is a Pauli X operator. Okay. So, I can rewrite this whole combination as, so this can be combined as particular notation I am going to use. So, there is a x to the power s. S is the result of measurement in a binary notation. So, it is in the set 0 and 1, this is 0 and this is 1. And another notation which turns out to be useful is related to this, which is t is equal to minus 1 to the power s, which maps this to plus 1 and minus 1. So, you can use either the binary label or the plus or minus label, whichever one that is. So, if I use x to the power s, it will convert this to this state, and then I do not have to worry about looking at both simultaneously. I just look at one part. And what is that one part? I can write it as a matrix, which is another notation I am introducing. It is j of theta acting on this 0 and 1, which is the two component vector which I wrote down, A and B, where this j theta is a unitary matrix it looks like that. Yeah, these are not together, this is a 2 by 2 matrix. I'm again, I'll normalize it. This at least I should put everything back in the proper shape, but there is a easier way to remember this, that this is actually the Hadamard matrix applied to the matrix which you will get by exponentiating sigma z. Okay. So, Hadamard is the usual 1, 1, 1 minus 1. If you multiply this, you will get that. Okay. Okay. So, the result of measurement is this, which means that the state moved from here to here, but simultaneously it got rotated by this particular matrix. This is the original state. Okay, so, gate teleported is x to the power s times j of theta. Okay. And when I use the ordinary teleportation, theta was equal to 0, then this just became the Hadamard matrix, and that is what I had in the formula I wrote down last time. Now, the important feature is that j theta is universal logic gate together with control Z. If you remember some of the logic gates which are used in the circuit notation, there was a 2-qubit gate. We could have chosen that as control Z or control naught, related by the Hadamard transformation. And then there are 1-qubit gates which were basically written in terms of polymetrices, and one commonly used construction is you use the Hadamard operator and powers of sigma z. So, the powers of sigma z most of the time are again truncated to going down to 4th root of sigma z, which is called the T gate, and other than that all the other gates are much simpler to implement. So, the T gate is some particular value of this, and beyond that you do not need anything else. So, you can convert all this circuit notation. Whenever the T gate appears, you can use this construction and write down everything which goes with a simple map, one notation versus the other. There is still something else which is useful to know, that if you take a circuit and construct a map which will convert each 1-qubit and 2-qubit gate in this format, then this will appear all over the place, in the sense that sometimes 1 qubit, sometimes CZ, etc. they are not going to appear in a specific order which is used in measurement based computing, but you can even get around that by using certain commutation rules, that CZ will appear all over the place, but I can commute CZ to all the other operators and make it always come, so that it is acting on the first step where it will get buried inside the initial state circuit. So there are commutations rules which you can now use, and they can be written down with rather simple construction. So Cz can be shifted to act on the initial state by and you need only two transformation. One of them is rather trivial because Cz commutes with all the Z operations rather trivially. And the second thing is, what does it do to X? And if I know what happens with Z and X, I can work out any combination which comes down, and that is now a two steps process because X is going to come. It may have some power like this, x to the power s, and can I decompose it in a simple manner? The answer is yes, and I need to have these indices in a place. So let me write it in some notation. This is on link ij, and x is one of the endpoints of the link. The operator is symmetric, it doesn't matter too much beyond that. But if this when the link and this location of x is a different place, they already commute. Only when they overlap there can be some difference, and the identity is that this goes through, but it produces a extra factor of z. So let us see how the circuit structure looks like. So here I say let me call this I and that is j. Suppose there is x. Remember, if s is equal to 0, that is one of the two outcomes. It's Cz on both sides, nothing matters. So only thing I have to check is what if s equal to 1. So there is x here, that is s equal to 1 case. Cz typical notation is something like this, and I want to shift it onto the other side. And what does the x do? It interchanges 0 and 1. So this is a control where if the initial state is 0, something will happen, but if initial state is 1, nothing will happen. And whatever this something happens or happen not is the transformation with the z gate. Okay. So let us see what this thing does. It's a circuit which looks like that, but first is z, then second thing is z is applied here, and then x is applied here. So, this x is applied, it has to basically remain on the first qubit, whatever it is. We are just trying to get it through this, but in between something happens. So, the change between this and this is because x shifted from this side to this side, the change should occur with an opposite values of 0 and 1 as far as z is to be applied on the second qubit. And in this case, z is applied where the initial state is 0, and to get that this gate is not going to act, but this z will produce that extra z factor which I need. And when 1 is there, nothing is going, no. Yeah, if 1 is over there, actually 1 becomes 0, nothing happens here. And if 1 is there, z will act here, another z will act here, z square is equal to identity, and you come back to the initial configuration. So, what this does is you can convert all gates one by one, keep on getting this kind of factors. The Cz will act all over the place, but then you commute all the Cz through all these extra measurement operators which you constructed to make it come and act on the right hand side, and then it is part of the initial state design. Okay. So, that is a kind of generic construction. It can always be done, and it is based on the fact that this is now the universal gate, you do not need anything more. So, as long as you can apply j theta, which is part of inside here, you commute through everything else. Cz acts only the initial